auf die anderen sind, gewastet werden.
Welcome back to microeconomics. So this is our last tutorial before Christmas break. I hope you're excited about the tutorial, but also for the break, I guess. So we're going to talk about game theory, proposition 6 today. Yes, so that's the first proposition on pure game theory, kind of, I guess. So we'll go through that. And since Christmas is coming up, there are some incentives today. Incentives play a big role in economics, so let's see if incentives work here as well. The idea is if you ask a somewhat reasonable question, or if you answer something, you get some treat. Okay? And for reasonable, the bar is pretty low. As an example, asking how the weather is today is not reasonable. Because it's beautiful and you can just look outside. But like, it's reasonable to ask like how does A follow from B? That's definitely okay. And it's first come, first served. For example, there's only one healthy Clementine left. So if someone wants to help this stuff, ask a question quickly. Alright, so that's the name of the game only for the day. Don't expect to the next year budget cuts are hitting hard. Nothing happens anymore. Alright. Good. So unless I want to ask something. Did everything work this time with the quiz? Did you get solutions as well?
Yeah.
No.
How are you?
No solutions? I should be there. Why is this not working? So I'll just upload them, okay? But I don't know if you could take it and everything is fine. Okay. I'll just upload the solutions. Why do I put them in online? It takes quite a while to put them on out before I guess. Just give you the solutions. Okay, fine. Okay, any other questions about anything else, I guess, before we start talking about the first exercise? Yeah.
Will we get a test exam?
I don't know, because I didn't think about it yet. I'll talk to Annie about it, I guess. I would guess no, but I don't know. So no promises about anything. I'll check. hear the exam. Okay, anything else? Okay, well if not, then let's start talking about this first exercise. So we consider this following two-player static game. Player 1 chooses rows and player 2 chooses columns, and payouts are, well, the first number goes to the row player, player 1, the second number goes to the column player, player 2. Oh, actually, one thing that I just asked before about it, there was one problem left on the last problem set. We're not going to discuss it because it's pretty much similar to what we did already, so it should be fine to work it out by itself. But of course, if you have questions, you can always ask me or put it on the Blackboard kind of forum as well, whatever is easiest, but we're not going to discuss it in here. Okay. So you're rather going to discuss this game, which is a 4x4 game, so each player has 4 choices. So I reproduced it here actually. So player row, the first player can choose between A, B, C, and D. And the column player 2, can choose between W, X, Y, and Z. You see I was very creative when I gave it names. Okay. That's the game we care about. And the first question then asks us to apply iterative elimination of strictly dominated actions, allowing only pure actions as dominated actions. So first question is, we need to understand what is, well, it's a whole thing, iterative elimination of strictly dominated actions. So what is a strictly dominated action? That's the first thing we need to understand. Remember the incentives. Canada is coming soon.
I think independent of what all other players are doing, it is never best response.
That's not the definition, but in some sense it's the correct answer. So, well, you get a treat anyway. Almost. So like, well, almost. The official answer would be action is dominated by some other action, I guess, if the other action is always, meaning no matter what the other players are doing, so that's the same, it's always strictly better. It's not quite the same as what you said, but it's very related. In some sense, it's the same. So you just have to check basically no matter what the others are doing. Like if you look at we ask the row player, if we check for domination, we just check across all columns is the number that corresponds to the first player. I guess the first one higher than the other. If we find one of those, we know it's dominated. Okay, so that's domination. Exactly. Iterative elimination means we delete them and then we do the iterative. So that's kind of clear. Yeah. Okay, first things, important things, sweet treats. What do you want for your answer?
I want.
You can choose a speculatius, you can choose a cinnamon star, you can choose the chocolate bomb, or you can choose a candy. Ha! That's it. It's gone. Alright, you see how it works? The incentives are, as promised, they will be delivered immediately. Alright. Okay, so let's try to solve this question. Anyone can find a strictly dominated action in this game. So, stare at it for a while and then maybe someone can find something. Yeah?
Why is strictly dominated by X for player 2?
Why? I mean, why is the question of why is that?
No matter if A, B, C, or D is chosen by player 1, Y always use a lower payoff than X.
Exactly. How do we know that? So we're looking, to be clear, we're looking at the second player, right? Because we're talking about his actions, which are the columns. Second player. So we need to look at his payoffs. So the second number, right? So we're comparing essentially these numbers 2, 4, 3, 1 to something else. Well, the proposal is to compare it with the W column, which has 6, 4, 3, 4. And now we compare it case by case. 6 is bigger than 2, 4 is bigger than. Wait, 4 is the same as 4.
I mean X.
Ah, you want X. Okay, good. So let's check X. 4 bigger than 2, 6 bigger than 4, 4 bigger than 3, 2 bigger than 1. Jackpot. You get something.
I mean,
That's not an answer. I didn't give you the option of nothing.
yeah, then that's cinnamon stuff.
crossing it out. We're deleting it. Okay, good. So now we've deleted it, can we find something else that's dominated in this game?
Now that y is deleted for player 1, strategy B is strictly dominated.
So the game is this is dominated, so by game, like you see something is dominated, you would need to dominate. By B, the game is by B. Right, so let's check this. Now we're looking at player 1, so we look at the first entries, right? And we need to check column by column. Right, so the game is 2 should be bigger than 0, yes, that is good. 1 should be bigger than 0, that is good as well. 2 is not bigger than 2 actually, but we crossed it out. It doesn't exist anymore, but that's all good. 1 is bigger than 0. So indeed, you get something. What do you want?
The chocolate.
Good, the second I can throw.
Yes.
Ah, perfect. Okay, good. So we delete B. Alright, so now we are left with kind of the smaller game here. Anything else you can delete? Takes a while, because the answer is no. You kind of need to check case by case. Everything now is a bit cumbersome, but once you do that, you should be able to do it. There's nothing more that you can delete. The answer is, we're left with kind of, if you want the proper answer, like written like, you would say the answer is, for player 1, we're left with A, B, and D. So it's a set A, well, A, B, D, A, B, and C. And for the other player, we're left with W, X, and the set. We deleted one action for each player. That's right. Okay. Now the next question to ask, we should do the same, but now we should allow dominance by a mixed action. First of all, we need to understand what it means to have a mixed action. What's a mixed action? Mixed action. Sometimes called mixed strategy.
It means applying probabilities to your own strategies in such a way that you make the opponent indifferent between his own strategies.
The first part was correct, the second no. The second part talks about something that's far more advanced for today. It's called Nash equilibrium. We're not there yet. The first part was correct. No, right? A mixed action is just a probabilistic assignment over your own actions. Like you can basically choose randomly between your actions. Like you can flip a coin, for example, and say 50-50, or you can be a bit more sophisticated and say that 30% I'm choosing A and 70% I'm choosing B. All that sort of things. Those would be mixed actions. And if we say dominating actions, allowing for mixed actions means that we need to check that maybe a mixture of your actions is better than something else. Right? And so the question is, we should do the same as before. So one thing that's always true if we allow because it says by pure or mixed, and technically you don't need the or because mixed actually includes choosing something for sure is still a mixed action. It's like a boring mixed action, but it's like just assigning 100% to something. That's in that sense it's still probabilistic, but it's a very boring probabilistic assignment. Right? So whatever we deleted here, we can definitely delete now as well. The question is, can we delete something more? So the question is, can some of the players, for example player 1, mix between 2 of his actions somehow to make him always better off compared to the third action? Can we do that? That's a bit hard. Yes?
I think now if player 1 randomizes between A and C,
Yeah?
and puts a relatively high weight on A, so I think something between 3/4 and 4/5.
That's very specific. Okay, that's good.
I think it needs to be between 3/4.
I think so as well. Yes.
Then that mix dominates B.
Right, that's absolutely correct. The question is, why is it correct? So what's the intuition? How did we come up with these dots?
C is the worst response to W,
Right,
and A is the worst response to X.
right,
But if we randomize, we can make it so that in both cases the mix is better than B.
yeah,
And if the other page is Z, then we're better no matter how we like mix between A and C, because both are better than B.
exactly. Right, like if we kind of look at B, it's kind of always okay actually, like it gives us 2, 1, and 1, or maybe 2 here as well actually. But we deleted that in the first round, so let's ignore that. So it's quite okay, it's 2, 1, 1, it's not too bad. But it's never great either, right? And it turns out if we look at the other ones, like there's always like, you know, either this one is great or this one is great. Or in this case both are great. The idea is maybe we can mix those two somehow together and make us overall better always. The claim was, well, we can do that with some mixing between 3/4 and 4/5. So let's try one of them. Let's do the mixture of 3/4 is the easiest choice. So we're mixing 3/4 of A and 1/4 of Z. So this is kind of giving us a new action in some sense. So we can calculate the utility, the payoffs we get for each of the actions of the opponents for this mixture. So let's see if we can do this. So if the other player plays the W and I'm mixing between A and C in this way, what's my payoff? My expected payoff. So by the way, this is where expected utility comes in as well, that we talked about before. Now I'm asking you to calculate the expected utility of a probabilistic thing that gives you choosing 3/4 A and 1/4 C. So if we do that, so I'm mixing 3/4 here and 1/4 here. And I'm asking if your opponent chooses W, what's your payoff? Yeah? 9/4. Let's see how we do the calculation, right? So we get, in the case we're choosing A, which happens in 3/4, we're getting 3. So we have 3/4 expected utility, right? It's probability times utility. So 3 probability times utility is 3. And with 1/4 probability of choosing C, in this case I get 0. Right, so we get 9/4. So this is this new action, you can write it here actually in some sense. And this gives us 9/4. This one we don't care about because we're looking at it. So this is the case for W. What if we do, if the other player chooses X, well, we have to do similar calculations, but now the players have changed. Right? With probability 3/4 be here, with probably 1/4 be here. So we get 0 times something, and 5 times 1/4, so this is 5/4. Exactly. This one we ignore, we cancelled that already out anyways. What about this one? Well, it's 9 times 3 is, what is that even, 27? I guess, plus 2, 29. So this is kind of this mixed action that gives us these payoffs. 9/4, 5/4, 29/4. Now let's compare it back to the B case, because that's what we gave before. This will be dominating this. Is it true? 9/4 is bigger than 2.25. This is bigger than 2. What about this one? It's 1/25, bigger than 1. Very good. What about this one? 29/4, bigger than this. Clearly, it's much bigger than 1. Right, so actually, in the second round, we should have deleted this one now as well. So the first round was the same. We delete this actually. The second round, we delete this and this. Both of them we can delete. This one like before, but this one is new. Question.
get to this function, or just
To
like
get to these mixing things,
yes, just
Yes.
try to-
you need to write down a lot of inequalities, right? You say like, you're mixing, we consider for now that B is dominating, right? So this is okay, this is on the right-hand side, so to speak. And then you say like, well, I'm choosing A with some probability, that's kind of B. BA and 1 minus B C. Right, so just for an arbitrary probability. You can do these calculations like here, you get the whole row, which now depends on B, because B is not a given number, it's just a probability. So you would get a row with B's in here, like some functions of B. And then you get many inequalities, because this number needs to be bigger than this number needs to be bigger than this, and this number needs to be bigger than this. And then you check if all these inequalities can be satisfied. That's how you do it. And in this case, you would get that this is true for all B's, doesn't matter. This one says it should be less than, no, bigger than 3/4, and this inequality would gives you less than 5/4. Something like that. 4/5, sorry. That's how you're going to get this range.
I think it's 2/3, not 3/4.
What?
It's 2/3, not 3/4.
Okay. It's in the middle, I guess. But yes, you get many inequalities. And you get as many inequalities as columns you have to consider. And then you have to check if these inequalities can be satisfied. So it's a bit cumbersome. That's the general way to do it. Any other question? Okay, if not, we move on. Can we delete something? Now. Is there something more we can delete? Yes.
I think W and X both weakly dominate Z, so I guess a combination
That's a very good one. So you say
be dominating Z, I guess.
X and Y.
No, W and X both weakly dominate Z,
Right.
so a combination out of them should be strictly dominating Z, no?
Very good. Right? So like this argument is actually different now. It says like this weakly dominates this. What does it mean? Weakly domination means that you get inequalities that are going in the right direction, so to speak, but allow for indifferences sometimes. That's exactly what happened, right? 6 is bigger than 4 strictly, but 3 is the same as 3. I think here it's the other way around. 4 is the same as 4, but 4 is bigger than 3. So now the idea would be, well, if you mix them a little bit, maybe you can actually use this mixture to create something that's always better. Right? And indeed, maybe you can see that if you do it 50-50 here, you can do it. If you mix 50-50, you get 5, which is bigger than 4. If you do 50-50 with 50-50, you get 3.5, which is bigger than 3. Right? So great, we can delete Z. So we're left with only these cases. Really. Right, so just to recap, first round was the same, second round was already we do, third round is the delete the same. Anything else we can delete now? So we only left with these guys, right? There's nothing we can delete anymore because all of them are kind of good choices sometimes, right? If the opponent chooses W, then A is good. If the opponent chooses X, then this is good. And the other way kind of around as well. If A is chosen, then this is good. And if X is chosen, then this is good. So we can exactly. So that answers our second question. Now I owe some of you, I guess, some sweets. I forgot about that. So let's do this important part now. You were last. What do you want?
Schokolade.
You answered something. What do you want? They're organic. I know that. You answered something as well. You answered something as well, right? What do you want?
No, my answer was wrong.
What?
My answer was wrong.
Your answer was wrong?
Yeah.
Partially wrong. I think that for Christmas it's okay. Exam maybe not.
Then I would take another chocolate.
No.
Thank you.
Good. Very good. Okay, so now we get actually this much smaller set right before we have this, and now we are left with this was question 1, I guess, and this was question 2. We got A, B, AC, and WX. That's the second question. Now the third question asks something very similar. We should actually start with the smaller game from the very first round. So after deleting what we have deleted, kind of, which was this guy. And this guy in the middle, we deleted this one as well. And this one's back again. Okay, so now we're starting with the smaller game. And now in the smaller game, we should start doing iterated deletion, allowing for mixed actions again. Right? So what can we do? If we just look at this game, that's the game I give you on the exam, and ask you to do iterated deletions allowing for mixed actions, anything you would delete.
B is dominated again.
B, but the same argument, B is dominated. And then by the very same argument. So in the third round, so we did 2 rounds already, now that's the third round, I guess, we did this, and then in the fourth round we will do this. Like before. And we end up at the same place. So that's a general thing that, you know, maybe you forgot something to delete, like maybe you did first iteration only by pure actions on the exam, and it's a very big game. And then you read, oh my god, Gabriel wrote mixed actions, now you have to restart everything. This basically says, it doesn't matter. Don't restart, just keep working. You can always do it. You always end up at the same endings, no matter what order you do. Okay. So with strict domination, you can do it. You don't have to worry about these things. And there is a concept that's also called iterated deletion of weakly dominated. Actually, we talked about weak domination already. There, it does matter how you do things. If you do it in different orders, you might get very different predictions. So that's why it's very different. Okay? But with the strict one, everything is nuts. You don't have to worry about any order kind of things. Okay. That's, I guess, the takeaway from this first exercise here as well. Great. Questions? Proteinfrei, laktosefrei, ohne Weizen. Danke sehr.
I don't know too much.
very simple kind of game actually. Not even a proper game, I guess. Alright, so now we have this very simple thing given. R, and we're only given the payouts of player 1 actually. So player 1 can choose the rows again, he chooses the A, B, and C, and he gets the following payouts 3, 0, 2, 2, and 3, 0. That's what we have to consider. Now we are having actually something more general, but kind of related to the question we had before. Now player 1 thinks that with probability P, player 2 is choosing F. Okay, so this happens with probability P, which automatically means this happens with probability 1 minus P. Okay. Now the question is, we should compute what's the expected payoff for choosing A, what's the expected payoff for choosing B, what's the expected payoff for choosing Z. Okay? This is actually, if you think about, not a game theory question, it's an expected utility question. Okay, because it's really just, we have to do some expected utility calculations. So let's figure this out. What's the utility of player 1 if he chooses A, given that he thinks player 2 is choosing L probability P? So we have to do some expected utility calculations, which is always the same in principle. We're summing across all possibilities, probability times utility. Right? So in this case, what is it? Three. That's it?
Yes.
Any other answers? Multiplied by P, exactly, right? We have to do the expected utility calculation, which is probability times utility. This is the utility part, multiplied by the probability, which happens with, in this case, we are, in this case, with probability P. So we multiply by P. Don't forget about the other part, which is, 1 minus P in the other case, but that's 0, so the actually have to go.
I thought it was given as you already decided on
No. So the question is more like, you're a player, they're a player, okay, and you're thinking about what should you do, but you're uncertain about what your opponent does. Is he playing L or is he playing R? Right, that's the uncertainty you're facing, and you think with probability B is playing L, and with probability 1 minus B is playing R, and that's why. That's why we get this. 3B. Okay, questions? So let's do the next one. What's the utility of choosing B given B? So again, the row player thinks with probability P, the other player plays L, and the other probability 1 minus P we are in R. But he's choosing B himself, the second row. So what's his pair?
2 times P plus 1 minus P2.
Exactly. 2 expected utility, or probability times utility, plus 1 minus 2. But if you see, this is just 2. In fact, if you just look at the table, you don't even have to do calculation, right? Because if he chooses B, you can see from the table the team always gets 2 anyways, no matter what happens. That's how his pair should be. Very good. Last part. the utility of choosing Z given this belief? You want to answer? Or?
Yeah.
Yeah.
0 times p
Yeah.
plus 1 minus p times c is equal to 3 minus 3p. Or yeah, like that.
Yep, absolutely correct. Very good. That's the answer. So we finished this question, so it's time for some sweet stuff again. What do you want?
One little piece.
Some tempo, speculatius.
Speculatius.
One again. You want one of those? And 2 tricks over there. Nothing. Because there's nothing really. I was only one camera man, sorry. I had more, but the undergrads liked all the camera lines before, so I didn't anticipate that.
And one such a vision assumption is not true.
Yeah, I guess not. No. I guess not. That's how it goes with theory. Doesn't work. All right. Anyways, that's the first part of this question. Of course, it's pretty easy. So let's go to the next one. Now you should ask for which p. So which? So this uncertainty parameter in some sense, right? For which of these uncertainty parameters is each action A, B, C a possible best response? Okay. So we should in particular show that P is not a best response for if we are at extremes, that the probability is either 0 or 1, and we should say show that it is a best response for some particular P that's in the interior. So the question here is really, the only thing we need to understand here is one thing that's from game theory is what is a best response?
Given a certain strategy from the other player, what strategy to play yourself to maximize the activity?
Exactly. I personally don't like the interpretation much, but that's how it's usually done. Exactly. I would not say it's the strategy of the opponent, it's more like my belief that I have about the opponent. But that's, you know, just not. It's not only just interpretation, but anyways. Right, so the other player is, you know, doing something, like, or I believe he's doing something, like here, either N or R with some probability, and the question is, with that belief that I have, or given his mixed action himself, what should I do as a best response, meaning what action should I choose to maximize my expected utility? Right? So we know the expected utility, so we just have to compare these numbers, and we need to check when is one, for which piece is one bigger than the other. Right? So how can we do that? Let's see if A is sometimes, or is A bigger, the utility of A, given the belief P, is this bigger than utility of choosing B, and also bigger than utility of choosing C. And because we are now for weak ones, we should take the one. Right, so this would say A is better than B, better than B, better than C. For a given probability distribution, given that it is P. Let's see if we can figure it out. So the first one would say that when B is bigger than 2, it's the same as saying B is bigger than 2/3. And this one says when B should be bigger than 1 minus 2. Three cancels out. So we are left with B should be bigger than 1. So now the question, for which of those beliefs do we know that A is the best response?
to be bigger than 1/2?
Yes, but that's not enough.
But it's bigger than 1/2, it's also bigger than 2/3, no? Or
Goes the other way around, or am I completely mistaken? No, this is the bigger number, right? 2/3 is bigger than 1/2, so we need
yeah.
we need this
yeah,
one.
sorry.
I get confused about this inequality myself. Right? But you take the bigger one, right? Why? Because if this is true, then this is definitely true. It's not the other way around. If this is true, we don't know if this is true. But we want both of them to be true. Right? So we need P to be bigger than 2/3. Then we know A is the best response. For any P bigger than 2/3, A would be the best response. What about checking when P is the best response? P is bigger than A. Now checking if we can make B the best response sometime. Well, the first one is which is the same as here, just reversed. Right, so we get the reverse inequality. B should be less than 2. This one is different. Now we need to ask if 2 is bigger than 3, 1 minus B. Now we get bring this to the other side, then we have 1/3. So this should be now again, we have two inequalities, and it says we should have B be less than 2/3 and B should be bigger than 1/3. So can we find a B that actually satisfies both of them? So we need to satisfy both of them, right? Because we want to make sure that B is bigger than the A and bigger than the C. Both of them should be true. Can we find a B that actually satisfies both of them?
A P that lies in between 1/3 and 2/3.
Exactly, right? Choose any P that's in this interval, actually. That works. Like 1/2, for example. Yeah.
But what if my P is 2/3 and then
If it's 2/3 or 1/3.
2/3?
So we aim in this kind of knife edge case here, right?
Yeah,
This is what?
because then A and B could be the
Absolutely correct. Good question. You could have more than one. That's true. But that's response. Totally okay. In fact, sometimes, and it has to be sometimes actually, often at least, that at some particular point, like here it's exactly the 2/3 point, for example, the two things are up to. Exactly right. All right. So now we are left with when is the C option the best option? So we have to do the calculations. Now, without doing any calculations, do we know already from what we did so far when C has to be the optimal choice? Best response.
C smaller than 1/3.
B smaller than Exactly. Why do we know that? Well, first of all, we can do the same calculations kind of and verify. But it has to be, right? Because we know already what happens if P is bigger than 2/3. Then we know A is best. We know what happens if P is in between 1/3 and 2/3. We know that P is best. But there's only 3 choices overall. If none of the other 2 is the best thing, then it has to be for the other cases that C is the best. Just has to be, because there's nothing left. So that's how you can do that. As a side, useful thing to sometimes as well is you can actually draw these guys, these expected utilities, and then you see it in the figure as well. How can you think about it in a figure? So we're drawing something like here to the expected utility, and here we have P, so that goes from 0 to 1. And you can draw these lines. These are all lines actually. So this one for A is a straight line with slope 3, so it's very steep, starts at 0. This looks like something like this. That's the line corresponding to choosing A. The same thing for the line choosing B, which is a very boring line, it's a straight line, well, left line, I guess, equal to 2 everywhere, so it's something here. B. And then we have our third one, which I don't know the color, which is, let me just make sure I draw everything correctly. I just screwed it up already. So it's the A line, the B line, and the C line looks like something like this. If B is 0, then this whole thing would be 0, right? Sorry, this would be 3, so we're very high up. Then it will go down to 0 here. This one is the corresponding to C. And since we're maximizing expected utility, we're just always looking at the highest parts, right? So in this region here, it's actually 1/3. C action is the best. And in this region here, it's here the B action is the best. And here A action is the best. So this gives it. And you can see actually from the figure that they are always, well, not always, but very often there are points where you're just indifferent, right? Here you're indifferent between two things. Both of them are optimal. Here you're indifferent between these two things. So this happens as well. But you have multiple choices in the best. So this is one way to think about it. A bit more graphically, I guess. Questions? Who do I owe something sweet? We'll have to do it right away again. Who wants something sweet? Who didn't get anything sweet yet? Who wants something? Easy way to get something. You could have answered that question actually, you would have gotten something. Okay, no questions. Then we'll move on. Right, so now we have shown actually part B, and we figured out the best response. So now we should show that B is not strictly dominated by any mixed action. Clear. Okay, so this is not quite the same, but it's sort of related. It's actually related to a question we had before in the first exercise, how we can see in general that something is strictly dominating something else. Alright, so now we want to check that B is not strictly dominated. Right? So let's write out what it means for B to be strictly dominated. Potentially it can be dominated by a mixed action, right? So if we're looking for B to be dominated, it can be dominated by A, it can be dominated by C, or it can be dominated by a mixture of A and C. In principle, it could be also dominated by a mixture of A and B. But if you think about it intuitively, this can never really work. Like if you really want B to be dominated, then it has to be that it's a mixture of the other two. Because if it's dominant, it means it's really bad. So if you mix it with something really bad, then clearly this is not so good. You would try to do something else. It's kind of dangerous. So we only have to check that you're mixing between A and C, and we want to check if we can get something that's always better than B. Okay, so let's write down the probability. Let's say you play, now we're mixing along the rows, not along the columns, because it's a mixed action of player 1. Right, so now let's say the probability Q be here, and the probability 1 minus Q be here. So if this is true, so we get actually here, this is our new mixed action, QA is 1 minus QC. They give us some payouts. What are those payouts? If the other player chooses L for sure, so we're in this column, what's the payout of this mixture? I'm mixing the probability Q, I'm here, probability 1 minus Q, I'm here. So what's my expected rate? Rate Q, right? It's 3 times the probability Q plus 0 times the probability, 0 times something is 0, so it's. What about this case? When we have this column here, the probability Q will be here, probability 1 minus Q will be here. So what's the probability? What's the expectability of this mixture? This is 0, right? So we don't care about this. This is 3 times 0. So this is what this mixture gives us. And now we want to show, or not show, that this must be big. We want to find some Q that makes this bigger than this and bigger than this. Then we would have strict domination. Right? This is bigger than this and this is bigger than this. So let's see if we can find a Q that does the job. Right? So we want that 3Q is bigger than 2 and 3 times 1 minus Q also bigger than 2. Right? So this is the first column, this is the second column. First column, this comparison, second column. Let's see if it works out. Let's rearrange. Q should be bigger than 2/3. Let's rearrange this. It's 3 minus 3Q. So we get Q should be less than 1/3. Alright. So that's the answer. Indeed, B is dominated by a Q that satisfies this. Right? If we find a Q that satisfies both of them, we found domination. Can you leave it at this? Or is there something wrong or missing in this element?
You can't find one single Q that satisfies both.
Exactly, right? We need to satisfy both inequalities at the same time. And this one says, well, it should be a number that's big, and this one says it should be a number that's small. A number cannot have these properties today. That cannot be bigger than 2/3 and at the same time be smaller than 1/3. That's just not possible. It's one number. Right? So this is impossible, which means we can never find any mixture that makes this strictly dominant. So indeed, B is not strictly dominant, as we wanted to show. Because this cannot be true.
Wouldn't it have been enough to just show that for P equals 0.5, B is the best response?
Absolutely. Very good question, because that's my point I want to make with this question. So it seems like, and there was, I think the first question of today, the first answer was kind of alluding to something like that as well, that there seems to be a connection between strict domination and being a best response sometimes. And in this case, we see that B is a best response sometimes, but we see also it's not strictly dominant. And the same is actually true for A and C as well, if you think about it. And indeed, at least for two players, it's a very tight equivalence. There's a statement, it's actually a famous theorem, actually a lemma, I guess. In game theory, it's called Peirce lemma, and that says an action is strictly dominated if and only if, so it's really the same, to say you can never find any belief, any P, that makes it a best response. So if it's not a best response to anything, then it has to be strictly dominated. And you can go the other way around as well. That's useful because sometimes it's easy to see if something is dominated, but checking for something is not dominated is a bit ugly because you have many inequalities. Here it's not too bad. Sometimes you have many inequalities, but checking that something is a best response is relatively easy. Like in particular, you see immediately that C is a best response, right? Because it's a best response, it's just plain up. That's very easy to check. But it's, again, on the other hand, a bit hard to check if it's not a best response to anything. Right? So you can kind of go back. Tricky thing is, this only really works very nicely with 2 players. With more than 2 players, we'll have an example next. It gets a bit more subtle. Yeah. So that's exactly right. There's this kind of equivalence. They're very different notions. One is about you doing something that's optimal for you, right? And the other thing is just looking kind of case by case if something is really bad. So intuitively, they should be kind of related, but it's not clear. And it turns out that they are related very closely. And it's a very useful result. It's actually a non-trivial result. It needs actually some, not hardcore math, but some quite sophisticated math to formally prove that. But we're not going to do that, but it's good to keep it in mind that we can kind of, in that sense, go back and forth between these two. In particular, if you know that something is a best response, you know it's not strictly dominated. On the other hand, if you know something is strictly dominated, you know it can never be a best response. So this are 2 kind of ways to look at it. Any other questions? Yeah.
It's a really stupid question. Therefore, I don't.
The weather is a stupid
No,
question.
no, no. It's a stupid question. Wait for it. Therefore, I don't want to treat for it. But is there?
That's up to me.
Is there a reason why you're using different brackets for the 2 bullet points?
Oh, that's not a stupid question. It's a very important question and can absolutely reason that you actually have different symbols here.
Okay.
Because these are very different things.
Yeah.
This is a set, that's why they're in curly brackets, that has 2 elements in there, 0 and 1.
Yeah.
That means, in this case, I'm asking you to check for P being equal to 0 or being equal to 1.
Okay, so it's binary choice then.
It's binary things here, right? This one is a very different thing. This is an interval, an open interval.
Yeah,
It has all real numbers from 0 to 1, excluding boundaries. So this is a very big set, has uncountable many things. This is a very small set. So it's very different.
Oh, thank you.
Many people are very sloppy with that. I'm not. So whenever I write that, unless it's a typo.
That's good.
In this case, it's not a typo. So, no stupid question. What tree do you want? Finally, someone.
That's a shame.
All right. Any other questions about that? Then we move on to the second game of this exercise. This is a bit more complicated because we have 3 players. Now it's probably the first time we saw a 3-player game as kind of with this matrix representation. So you have to think about, usually we have 2 players because it's 2 players is very easy. 1 player chooses rows, 1 chooses columns. If we have 3 players, what the hell is he choosing? He's choosing his action. How can we think about kind of this kind of graphical representation? One is choosing rows, one is choosing columns, and the third?
One on the second game.
Yes, he's choosing actually tables. That's right. So you get a tree. actually it says here player 1 who is choosing the matrix. So we're choosing either this or this. That's what player 1 is choosing. You're either up here or down here. Now there are two other players. One is choosing the rows, L or R, and the other one, player 3, is choosing little l and little r. One is choosing still columns, one is choosing rows. Our player 1 in this case is choosing the matrix. Now talking about convention, here it's player 1 who chooses matrices. Often you don't see three player games too often because they're a bit messy already. It's often the third player who chooses the matrices, so player 1 still chooses rows, player 2 chooses columns, and player 3 chooses matrices. Here, because we care about player 1 only, I made him choose the matrix. So everyone usually agrees on how to write payoffs and who is choosing what. When there are two players, with three players is not quite common, so if you have to do it, maybe you want to write a short sentence about who is choosing what. So let's just skip it. So here player 1 is choosing the matrices. Okay? Now we have to consider. So now from player 1's perspective, who is choosing the matrix, right? He has actually the uncertainty about what his opponent is doing. Well, now he has two opponents actually. The second player and the third player. Right? So he is actually wondering with what probability do they choose a combination, right? With what probability? He's wondering, I'm player 1, say, and I'm wondering what probability do we end up, my opponents choosing little l and big F. That's one possibility. But there's also another possibility that my opponents choose, let's say, big L and little r. Well, they might as well also choose big R and little l and big R and little r. Those are the four combinations that they can choose together in some sense. Right? Those are the four options that my opponents, that's in the hand of my opponents. I cannot decide. It's up to them. Right? So my uncertainty is about those four things. Now this is an uncertainty about four things, but it has this kind of nice product. Right? It's like always two things, two things. Two things, two things. So we can actually write this uncertainty itself as a matrix. Okay? And with some probability here, some probability here, some probability here, some probability here. And it's just like corresponding to these guys. That's my uncertainty. That's how I should think about uncertainty. It's not one p, it's actually four numbers. Right? These are all probabilities. They should sum to 1. What probably end up here, what probably do end up here, what probably end up here, what probably do end up here. I don't need all the four numbers, I only need 3 because the fourth is always 1 minus the other. So it's a probability. So they need to sum to 1. That's the uncertainty. And now the question asks, actually, I'm giving you one of those beliefs, kind of like before, what I think about my opponents. It says with probably 1/2, I think my opponents will choose LL, and with probably 1/2, they will choose RR. So what we actually having is these conjectures and beliefs about what my opponents are doing. Probably 1/2, and here, 0 here, 0 here. That's what I think my opponents are going to do. Yeah. Now the question should calculate the expected payoffs by static utility for me choosing the first matrix versus for me choosing the second matrix. Okay? So that's what we have to do. So let's try to figure it out. What's the expected utility? If I choose the first matrix, which means I choose X. If I choose X, what's my expected utility? Two. Why? Let's see. So I'm choosing X, right? So we're in the top matrix. And I'm saying with probably 1/2, we're in the LL, and with probably 1/2, we're RR. So expected utility, 1/2 we're getting 2, plus 1/2 we're getting 2. write it out, or was it clear? Okay. So we're considering me choosing, I play one, I'm choosing matrix X, right? So that's the upper matrix. The matrix is my payoff matrix for X is R. So I'm saying I'm getting 2 in this case, I'm getting minus 2 in this case, I get minus 2 in this case, and I get 2 in this case. That's the payoffs that I consider. By choosing X, I get this payoffs. I don't know where I end up, because that depends on the others. Right? But if I would know what the others would be doing, then I would know what number I get by choosing X. Those are the payoffs. Now those are not the payoffs, those are the probabilistic assignments. Right? We need always 2 things in expected utility. We need the probability and we need the payoffs, the utility. So here we have 2 things, today was because we need 2. Yes?
Why are we considering our correlated belief true?
No, it's not about, nothing is about truth here. It's just we're saying you have this belief.
But in our expected utility, we're considering it to be true to have our payoff, no?
Philosophically, no.
Okay.
It's just, you know, you have that belief, and with that belief,
But why isn't it 1/4 each combination? I don't get why we consider 1/2 to be
I
true.
mean, like we will consider the 1/4 very soon. Just an illustration that in principle you could have this belief that with probably 1/2 we end up here, and with probably 1/2 we end up here.
Yeah.
What's the best thing to do? Right? That's what we ask. If you think that's the world, what do you want to do with it? That's what we ask. It's not about if that's the true world, that's just what you think, right? You think with probably 1/2 you end up here, with probably 1/2 you end up here. For whatever reason. I'm not saying this is true or wrong, I'm just saying this is what you think, so if that's what you think, what should you do? Right? And for what you should do, you need to first calculate the expected utility. That's what we do. So let's figure out the expected utility for choosing X, if that's what you think that will be happening. Right? And now we're doing the expected utility, so what does it mean? It's always case, summing across all the cases. We have 4 cases here. Probability times utility. Right, so we need to do that as well. So we have the first case, probably 1/2, times the utility 2. Next case, probably 0 happening, times the utility, minus 2. Then this case is also happening, probably 0, also minus 2. And then with this case, 1/2 gives us a payoff of 2. Now combining all of that, we get a payoff of 2. All I'm saying is, if you think that's how your opponents work in some sense, that would probably 1/2 you end up here, and probably 1/2 you end up here, then you get a payoff of 2 if you choose X. An expected payoff. That's the payoff you get for choosing X. Now, what's the expected utility for choosing Y? Meaning you're choosing the second matrix over there. Lower one. 1, right? You can literally do the same thing again. You write down the payoffs, they look different now, you do this calculation, and you get to 1. Or you stare at it for a minute or so, or less, and you see, well, it doesn't matter here, because no matter what the opponents are doing, I'm always getting 1. Right? So by choosing Y, actually, I'm always getting 1. So my payoff better be 1. But you can verify, it should be the same, of course. Not something like that. Right, so now we see that if you think that's how the world works, what's your best choice? You want to choose X or you want to choose Y? X. Right? Because X is big. So we see actually in this case, we would say X is the best response to this particular belief or mixed action of the opponents. Right, so B is the best. X is the best. part D at least. Now to the very last part, we should compute the marginal distribution. So now we need to think about some probabilistic things again. That's not really what game theory of this, what's called a correlated distribution, and consider from that we should consider the independent distribution. So now we need to think what that means. So this is what's called a correlated thing, because if you think about what it actually means, is that the opponents, they're choosing very correlated, right? They're choosing the same actually in some sense. Whenever this player, the row player chooses big L, that means the column player chooses little l. And if this guy chooses R, then the other guy chooses R. So they're always choosing the same. Right? In that sense, it's correlated. In fact, it's perfectly correlated. That's why it's called correlated. But if you think about it, maybe, we did say usually in game theory people make their choices independently. What player 3 does should be independent of what player 2 does. This is not reflected here. That's maybe why it's not looks weak, because it doesn't have this independence property. Right? So let's figure out if we can, from this distribution, make an independent distribution that has the same marginal distribution, so meaning for just one player they have the same probabilities. Right? So in this case, the marginal distribution for player 2 would be that he's choosing L with probably 1/2 and R with probably 1/2, and same for player 3. L with probably 1/2, R with probably 1/2. There's one independent distribution that does that. Independence in probability always means just multiply our probabilities, right? That's what independent means. So if you would do that with actually making everything 1/4, then you would get that. This would be an independent distribution. And it has the same marginals. Why? Because probably the little l happens is 1/4 plus 1/4, 1/2. Probably the little r happens 1/4 plus 1/4. Probably the big L happens 1/4 plus 1/4, 1/2. Probably the r happens 1/4 plus 1/4, still 1/2. Right? So for each person individualistically, it looks the same. It's just about how they are working together. It's different. Now, player 2 and player 3 are really working independently with this view. So that's the independent view. And now again, we should ask, what's the best response to that belief? So we have to do the same kind of calculations as before. Let's start with the expected utility of choosing the lower matrix. Why? What's the expected utility? 1, right? We don't have to do any calculations here again, because it's always 1. That's the easy one. What's the expected utility of choosing the upper matrix, choosing X? With this belief. 0. How do we see that? Well, you literally can do sort of this calculation, or you just stare at this, right, and say, well, we are equally likely in each of those cases, and they're kind of symmetric in the sense these are -2, these are +2, so they all cancel out. 0. So now, what's the best response? Do you want to choose X or do you want to choose X or do you want to choose Y? Why? Why do you want to choose Y?
Because the expected utility is higher.
Yeah, 1 is bigger than 0, so this is bad, right? So what do we see now? Actually, it does matter if we have like these independent beliefs or not, right? If this one is not independent, it's a correlated belief, then actually X was really good. If we have the independent belief, Y is really good. Right? So with more than 2 players, well, more than one opponent, particularly, if you have more than one opponent, you have to worry about these things. That's kind of the take-home message. And just as a side, it won't be relevant for anything we're really doing in this master's course, but since we discussed this equivalence between best responses and best responses and strict dominance before, in 2 players it's always the same as that. With more than 2 players, it is also the same, but we need to allow for these kind of maybe strange looking things as well. that all distributions are here allowed. If you only look at the independent ones, you lose the equivalence. The cycle. If you allow for all beliefs, like these ones, you get the full equivalence again. If you only allow for independent beliefs, you don't get this equivalence. That's really a cycle. Alright, I guess we are for once quite on time, but it's also the Christmas tutorial, so I guess it doesn't matter if we finish a bit earlier. But unless you have any questions, then we're done for the day. After the break. And if you want to take some sweet stuff on the way out, there's still something left. But I don't want to carry it home. So.